Welcome to my presentation on Introduction to Rust Cryptography. Today is going to be just a let's code, let's hash sort of a presentation, so there's not going to be too many slides here. The agenda for today is I want to make a SHA-256 sum replacement. So I'm going to use the SHA-2 crate to do this, and that SHA-2 crate implements traits from the digest crate. So yeah, let me just jump into it and we'll start coding up so you can see me fumbling and bumbling along the way and maybe pick up not only knowledge from me doing it, but also knowledge from me making mistakes. So yeah, this is going to be a little bit longer than normal videos, even though the actual work here is quite small. So yeah, let me just jump into it. So the first thing that I'm going to do is I have a little starter project that takes care of a lot of the boilerplate code towards setting up criterion and setting up some unit tests and stuff like that. So I'm going to grab that project and turn it into the project that I'm going to use for this hash demo. And get into the hash demo area, get an init. And then the last thing that I'm going to do is I'm going to rename the project to hash demo inside of the cargo.toml file. All right, so let's start coding. Now you'll see there's pretty much nothing in here, so we're starting from scratch. Okay, so what we want to do is make a function which takes in a string, a reference stir to a file, open up that file, and hash the data and spew out the 256 bits, which represents the SHA-256 sum of the file. So our function is going to be public, and it's going to be called hash file. It's going to take a file name, and that's going to be a reference to string. And it's going to output a result to a array of U8s and 32 of them, which will represent our 256 bits. So right off the bat, I need to, first of all, just to get me compiling along, I'm going to put this in, and I'm going to open up my cargo.toml, and I'm going to use dependencies of anyhow and SHA2, and I'm going to import the anyhow stuff that I'm going to use here. And let's see if that compiles. And it does. Okay, so the next step is to actually get our hasher object thing to do the hashing. You'll see what I mean in a second. So I am going to set up a let hasher become SHA-256 new. So that's not going to compile because we need to import the SHA-256 hasher object, and we also need to import digest to get this new function. All right, still compiling. Okay, so the next thing that we need to do is open up the file to be able to read the data out of it. So standard file open, and we are going to pass in our file name, and we're going to return an error if there's something wrong here. Still up and compiling. And the next thing that we want to do is read in that data. So we want to read in that data into um, a vector of bytes to hold the data and be able to use it so that I can pass it into the hasher with the update um, function for the hasher. So I'm going to get a mutable vector going on here. So let's call this file data, and it will be a vec new, and I'm going to file.read completer's not working so well today. Because it doesn't like this for some reason. Could not find file in stdio. That's fs file. Okay. And we want to read to end, and we're going to pass our file data into that. And then we want to take that file data and pass it to the update function of hasher. So hasher needs to become mutable. And then we are going to hasher.update, and we're going to pass in that data. And then we're going to get the hash out of it by using the hasher.finalize function. So the thing is, this hasher finalize gives us this thing called a generic array. And we don't want a generic array. We want this a real like Rust array, not like a type which kind of manages data like an array. We just want an array because that's what we said we want. So in order to get this, we need to get ourselves a mutable array, and that's gonna, we'll call this return or ret, and it's going to be a U8 32 in length, and we will default initialize it. And then what we're going to do is copy from slice, and that slice will be that hash data. And then we will return an OK to the ret. All right, so let's see what we've got going on here. Does this compile? No, we have made a mistake somewhere. What is the problem here? Have I missed a semicolon? Have I... Ah, okay. There we go. All right, so now we are compiling. Um, the thing is, we don't know if we work properly. So a real kind of a bad way to test would be to just output data inside of our from our main program and see if that matches sum 256. So let's start that off first. That's the wrong way to do it, but let's just start that off. So in here we want to use lib, everything from lib, and then what we're going to do is um, we are first of all going to get ourselves the args. And we do this by standard env args.collect. And we have to give ourselves a type here, so that's a vector of string. And from that, let's check if the args.len is less than 2. Let's not enough args. But if it is long enough, then we can get our hash array from hash file, and we will pass in the args 1. All right, so now we've got this now we've got this array of bytes, and we can debug print that. So we'll cargo run and we'll pass in the data of the source main rs function itself. So we've got a bunch of bytes here, but this is kind of hard to read. So I think we're going to need another function here. We're going to need a function which takes the bytes and turns it into characters that we can print out on the console. So we want to make this a string basically. So we're going to make another function here called hex to string, and it's going to take a slice of U8s, and we'll just call that data, and it's going to output a string. And very simply, it's going to for D in data, it's going to format to a specified length hex character of that. And we need to get ourselves a string to actually return here. And we're going to get this as an intermediate value. And we're going to push okay, so now this should print us out a nice hex string that we're kind of expecting to see. So let's go ahead and use it. Let's try this again. All right, that's more like it. Now let's check to see if we get this hash. Let's check to see if we get this hash from SHA256 sum. SHA256 sum of source main.rs. And we do, but SHA256 sum also has this space, and it prints out the name of the file that we put in. So let's go ahead and add that to our code so that we are more in line with what SHA256 sum does. All right, and we need 2 spaces. All right, so we've got ourselves a rather untested version of SHA-256 sum written entirely in Rust. The thing is, we actually need to do some testing on this. So the first thing to do is determine where are we going to get our testing data. And the answer to that question is that the NIST, a government agency in the US. What is NIST? National Institute of Standards and Technology. NIST gives us a set of test vectors for SHA-256. So let's do a Google search for SHA-256 test vectors and look inside of their validation program. And if we scroll down, we will see that they have SHA test vectors for hashing byte-oriented messages, which is what we're doing right now. So if I click on that, it's going to go ahead and download SHA bytes test vectors 3.zip. So let me grab that from my download area, and I am going to put that inside of my test data. All right. Now, what we want to do is open up the SHA-256 long messages and get some data out of that so that we can make ourselves a file containing some test stuff. So I am going to open up, it's in test data, SHA byte test vectors, SHA, and it's going to be SHA-256 sum long message.rsp. All right. So what we want to do here is grab, so a message is the test vector, and the MD is the message digest. And that's kind of, if you pass this through SHA-256, you should get this as a result. Now, of course, this is text, but what we want our file to hold is the binary representation of this. So to get the binary representation of this, it's pretty easy on a Linux system. We're just going to copy this out. And we are going to use echo. We're going to paste that data. And we're going to use the XXD command line option, passing through a -P option and a -R option. Then we're going to pipe that into the file that we want the data to be held in. So we're already in test data, so there we go. So now if I take a look at test 1, you'll see that it's kind of gibberish garbage here, but if I XXD it, it is the same as what we get from here. Ignore the new line endings. That's just for visual to help you understand more visually. If I take a look without the -p option, you'll kind of see that it's just the bytes in the file. There's no new lines in this file itself, um, except where there's actually new lines from the data. But yeah, now we've got a test. We've got data to test against, but we also need to get that message digest and be able to write a unit test to be able to kind of match them going forward. So let's go back to our source code, and we no longer really need this. If you were making a professional project, you'd want to use more than one test vector. You'd want to use a bunch of test vectors here. But for this demonstration purpose, for this video, I'm just going to use one, and we'll understand that a real unit test would do more than just one test here. Okay, so back to the lib code, and I'm going to write a function called test SHA256 sum. So let's get the hash from a hash file, and we're going to pass in test data test1.bin, and we'll do an expect here. In lieu of a proper error handling here. Okay, so we've got the hash. Next we want to do is get that hash in string form. And then we want to compare this hash string to this message digest. All right, so does our test work? And it appears that it does. Let's do one more test here. Let's use SHA256 sum on that test1 bin and make sure that it is telling us that it's got the 3C59 blah 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 blah. And it does. And one last run here. Let's cargo run, passing in the test data test1 bin, and we expect to see exactly what we got from SHA256 sum. And we do. So we've got ourselves something to go about with testing to ensure that our SHA256 sum clone gives us correct outputs here. Now, the next thing that we should think about is how fast is our function here? How fast do we compare to SHA256 sum? So let's use a tool called Hyperfine to be able to answer that question for us. So we're going to get ourselves ready on the command line so that we can rerun this over and over again. So I'm going to cargo clean, cargo build, release, and then I'm going to use Hyperfine, and you can see that I'm using Hyperfine with warmups. I'm doing 4 warmups, and I'm going to rerun Hyperfine, or I'm going to rerun my binary 10 times, and I'm going to pass in my test data test1.bin. So why is it not running multiple times here? Is this that? Oh, it's just super fast here. Let's use a much more a longer run test. So I've got some Linux ISOs available to me, and I have them in my storage area ISOs. And let's use Alpine to test this against. So this should be slower and thus not immediately finish. There we go. So we take about 135 milliseconds to do this. How fast is SHA-256 sum? So let's use Hyperfine the same way. And we're going to use Alpine. And it is much faster than our implementation. So what can we do to speed up our code? Where are some of our bottlenecks? Well, the easiest thing that we can do is go into our cargo toml and set ourselves up a profile.release, and we'll set our opt level to 2, and we will turn on LTO. So let's see if that helps us any. Not really. So the next thing that I like to do is use strace to see kind of what's going on with the system calls. How many times is our project using a system call, knowing that system calls cause a context switch, which can slow down our application. So to do this, we can use strace. So I want to strace on our target release bin, and I will strace that. And you can see if I actually pass this through WC, you'll see that we're calling 78 system calls. And you know what? It might be better, it might be a little bit more demonstration if I use a bigger ISO for this. So again, we're only using 78 system calls. But if you notice when I run the strace call, there's a little like blip between system calls here. Did you notice that? The reads seem to take a very long time. And the reason why the reads took a very long time is we are getting a ginormous amount of data here. Let me plug that into a calculator and we'll see how much data we're getting in this single read. Let me copy that. So we've got that many bytes. So how many kilobytes are we? And how many megabytes are we? Okay, so we're nearly 2 gigabytes of data here in a single system call. What does SHA-256 sum do with its system calls? So the first thing that I want to do here is pass it through WC to see how many lines of text there are. And there's a lot more system calls here than ours, which is a little counterintuitive because system calls cause a context switch, which should slow things down, but they are faster than us and they have a heck of a lot more system calls than we do. So let's look deeper into what they are doing here. And you'll see that they're calling read over and over and over again, which with a much smaller amount of data. And they are using hex 8000 as their amount of data that they're getting out of here. So I think the learning here is that we shouldn't call one single read. That one single read is probably our bottleneck here. Let's do something more along the lines of what SHA-256 sum is doing. And what they are doing is they are having a very specific size that they're reading from the file over and over and over again until the file is end of filed. So let's have ourselves a size variable the same as what SHA-256 sum is doing. And instead of having just a ginormous vector here with no end by using the read to end, let's actually have a vec where we initialize it to 0 and have the specific size of the 32,000 in it. Now this means that we have to keep reading over and over again rather than reading in just one shot. So in order to do that, I'm going to do a loop, and I am going to get the amount of data read as from the file.read, and we will again pass in our file data, but this time read is going to read at 32,000 bytes at a time, 32 kilobytes at a time, rather than the 2 gigabytes all in one giant read call. And we'll see if that helps us. But this also means that I need to hash update over and over and over again. Now, how do I know when to stop this loop? I know when to stop this loop if my size, this amount of data read, is not equal to my size. Because that means I got less. So if I get less than what I wanted, we've hit the end of file, and less also includes 0. 0 is less than 32 kilobytes. So let's do an if check here. If amount of data read is equal to size, then we will do our hash as normal. Else, we will hash we will update data into the hasher of our file data, but we will break from the loop in this case. All right, what's it saying here? All right, so if does this compile? No, why not? Because we need to do that. All right, so does this pass our cargo test still? The answer is no, it doesn't. Why doesn't it? Well, the thing is, because I am reusing this file data without reinitializing it to zeros, if I get, say my size here is 16, but I only read 2. So that would mean that the first 2 bytes of file data will contain the data from the file as per this read call, but the other 14 bytes will contain old data. So we don't want that old data to be hashed again, because that will obviously give us an incorrect result. So what I'm going to do here is I'm going to say that we go from 0 to amount of data read. So I only want that slice. I don't want the full slice. I only want those first bytes that correspond to the bytes actually read out of the file. Let's give that another cargo test, and you'll see that everything is passing here. So does this speed us up? Yes, it speeds us up, and does that get us in line with SHA-256 sum? Yes, it does. So great, we've now got ourselves a hasher that is just as fast as SHA-256 sum. Awesome. But we can do more. There is there is this SHA-256 sum application that is used to test the validity of files. But there is also another program called SHA-512 sum. So I think we can make this code do both a SHA-256 sum and a SHA-512 sum as well. So you'll notice that the SHA-512 sum is bigger because it's 512 bits in length. So let's another thing that I want to do is I don't want to use a different function. I want this one hash file function to do both 256 and 512ing for us. So the way that I will do this is I will pass in, or I will template this to take a D of type digest. And that means that our test needs to pass in a type digest, and that will be for this SHA-256 sum. It will be the SHA-256 thing here, and I'm using the turbo efficient correctly, so there we got it figured out. And after that, let's see if we pass our test again. And no, I didn't update my main. And another thing here is that I don't want, from my library, I don't want my clients to have to re-import this SHA stuff. My clients should not have to care about the hashing crates that I'm using. So I'm just gonna pub this. And you know what? I'm gonna get this out of my area here. All right. All right, and we're still passing our tests. Great. Let's make ourselves a SHA-512 subtest. Now, we are going to have to use different test data. So let's open up those vectors from NIST again. And in fact, I'm going to get this out of my way here so we can see a little bit better. So let's open up the test vectors again, but this time I want the SHA-512 long message stuff. And I should have opened that up in Neovide. So again, I'm going to grab this message. And I'm going to use echo to pipe it through. And I'm going to create that test 512 bin. And let's use XXD to test that 512 bin. And the SHA-512 sum is getting the same as this message digest. So let's copy the message digest. we are using test. All right, so what's going to happen here? It failed my SHA-512 sum test. And of course it did, because I am still using SHA-256 to do the things. And I want to use a D here representing the digest type that we passed into the hash file function. So what happens if I cargo test this? Still failed. And that is because it's panicking. It's panicking because I am using an array of only 32 bytes in length, but a SHA-512 gives us 64 bytes of data, representing 512 bits of data. So we've got a problem here. How am I going to represent that in one invocation of hash file, I want an array of 32, and in the other iteration, I want 64 at compile time? This is where there is two ways of doing this. The first way of doing this is to use a const generic, and that's what I'm going to do at the start here. The second way to do this is to, instead of returning an array, we can return a vector. And we'll do that later on in the video. So how do I use a const generic to get what I want out of this? Well, I'm going to do a const n, and it is going to be a usize. And in here, I'm going to use the size of n for the result type. And then I am again using an n for the thing that I'm going to return. But you'll notice that default is saying that there's a problem here. And that's because there is no default implementation for generically sized arrays. There is default implementations for arrays of 0, 1, 2, 3, 4, 5, 6, 7, all the way up to 32. But 33 and beyond, there is no default implementation for, and therefore there is no generic default implementation. So we can't use this method to initialize ourselves. So the easiest way to do this is to use some unfortunately it's to use some unsafe code. And it's to use this maybe uninit module function. So it's uninit dot assume init. And then we're going to pull this in. And then we need to update our tests to say, with the SHA-256, we expect a 32 byte array. And with the SHA-512, we expect a 64 byte array. And again, inside of our main, update it. And do we compile? Yep. Do we pass our tests? We do. Awesome. So now we have a generic summer, a generic SHA sum. So it's both 256 and 512. One last thing that we need to do inside of our main program is to go, if you have args.len equal to greater than or equal to 3, and the args2 is equal to 512, then we're going to do a 512 sum. Otherwise, we are going to do a 256 sum. Why didn't I like that 512? Oh, that's weird. All right, so we've got the same thing going on here as SHA-512 sum. All we need to do is pass in this little extra variable at the end of our command line, and we do 512 instead of 256. So again, let us see how fast or slow we are against SHA-512 sum. So let's go back to that big long hyperfind thing. And in here, instead of just doing the 256 sum, let's do a 512 sum. All right, and what is the speed of SHA-512 sum? So we are again quite a bit slower here. Is there anything more that we can do? Spoiler alert, spoiler alert, no there isn't. This is kind of the limit speed that I have gotten to over my various testing and doing this kind of project. I'm not sure where the problem is, but let's pretend that I don't know the answers yet. How would I go about seeing how fast we are? Seeing if there's anything that we can do. So first of all, our cargo TOML is doing the optimization stuff here. We are basically can we maybe do a FFFF on this thing instead of just 800? Does that help us at all? Not particularly. All right, so what more can we do? We can start looking at flame graphs to see where. Well, let me show you what a flame graph is, and you'll see it. You'll see why it might be useful to you. So first of all, flame graphs won't be good for us with these optimizations on, and in fact, I want to make sure that we're at optimization level 0, and I want to make sure that we have debugging inside of our binary so that the flame graph perf stuff can understand it. So in order to run flame graph, first you need to cargo install flame graph. And to do that, you just cargo install flame graph, and the -- force will ensure that you've got the latest version. The next thing that you want to do is you want to make sure that this specific file inside of the proc file system is set to -1, and that will allow all users on your machine to be able to do perf testing. So let's check out what my if my perf event paranoid is set to -1, And it is, but if it was not, I would do an echo -1 sudo t into that file to make sure that it's -1. All right, so the next thing that we do is we just run a cargo flame graph, the name of our binary, and the data that will go into it. But there is a weird problem here, right? This is, well, actually, let's watch to see what goes on. Okay, so we've got a file called flamegraph.svg, and I will use Firefox to open that up. And I will show it to you on the screen. So this is what we get. We get kind of a set of the functions that perf is able to determine that we have called while executing. But you'll see that there's not a lot in here. We've got, we did an open system call. Perf executed our function, and that seemed to take up, the execution of our function seemed to take up a lot. There's not a lot of data here that we can go on, because I know for a fact it's not open that is taking up the majority of our time here. It is in fact the update function, the hashing function, which takes up the majority of our time. But what more can we do here? Is there more stuff that we can do? We've got ourselves an opt level of 0. We've got our debug true. We've turned off LTO. Okay, so this is an unoptimized build. We want to do this on an optimized build. Can you just pass in release to this? No. Cargo flame graph help. How do we run optimized with you? What if I just... Oh, that's why. That's why. Because I've said don't be optimized. So the one other reason is that that we're not getting good enough data is that we're only running our hash function once, and it's just not enough iterations for the flame graph to give us some good data. So let's change this out such that we run it in a for loop. Right, and what does our flame graph look like now? Is there more data to this? Yeah, there's more data. So you can see that now we're seeing that and actually one last thing here, I need to run this properly. So now you can see that 50% of our time, and you can zoom this in, and 50% of our time is in this compress x86 AVX12. So yeah, nearly half of our time is spent doing the hashing itself, and that's not something that we can deal with. That's on the Rust crypto libraries to address or not address, depending on what their priorities are for the library. Yeah, there's not too much we can do in here. Finalize is taking up 5.6%. our hash file itself taking up 11%. So yeah, there's not much we can do to actually improve the performance of our code. It's upon the Rust crypto libraries to improve this. But clean up here. What we can do is clean up our own code so that it's a little bit nicer. So one of the things I really, really dislike is this unsafe call. So in order to get rid of this unsafe call, how am I to initialize my array here? Well, the way that I would initialize my array is to not use an array, is to use a vector. So before I actually do this, let's one more time run this through Hyperfine and remember how long it takes us to hash this Alpine ISO. Oh, and let's make sure that we've got our optimizations turned on and we are not in debug. All right, we're at, 220, somewhere between 200 and 220 milliseconds. So let's just remember that. If we, go way out to like 270, we've made a problem here and we need to revert. But for right now, what I want to do is instead of returning an array, I want to return a vector. So with a vector, I no longer need to set a constant size. And I am just going to return a vec of U8. That means that this guy can be a vec of 0 to size. Now, where do I get the size from? Luckily, we can get size from our d_as_digest, and there is a function called output size. And that's going to give us either the 32 bytes or the 64 bytes, depending on which digest that we passed in here. So now we've got the correct size. We've initialized it. And we will copy from slice it. Now we need to address some of the compilation problems that we've added in here. We no longer need to say how long we expect our array to be because we do not have an array. And same in our main. All right, do we compile? Yes, and we no longer need that maybe uninit. All right, let's cargo test. And we pass all our tests. And do we get the basic output that we expect when we run our function against SHA256 or SHA512? And it's the same data there. And it's the same data there. So, and one last test is, did we make our application slower? So we said it was around 200 to 220 milliseconds, and our window is up to about 270. So yeah, it's in the same amount of time as before. We no longer have the unsafe code in here. So it's a little bit nicer to work with. And yeah, we've got ourselves a clone of both SHA-256 sum and of SHA-512 sum. In future videos, we can look at doing password hashing. So, a warning, this hashing is not safe for passwords. You need a specific type of hasher called KDF2, password-based key derivation function version 2, to properly do hashing of a password to ensure that it's storable on a device. Um, in the next video, we can take a look at doing some PBKDF2 if this video has gathered enough interest. So thank you for watching. I hope you've learned something. I hope you've learned something about hashing, about Rust, and a little bit about Linux too. So yeah, have a good day. Thank you.